Hey class, hi and welcome. Let's see. Looks like I got a question from chapter 17, number 37. So, dealing with sound waves here. Let me read it. It says a tuning fork vibrates at 512 hertz and falls from rest with an acceleration of 9.8. So maybe I'll kind of make a little tuning fork here and just say, all right, we strike the tuning fork and it vibrates. This would make waves going down and waves going, well, in all directions. But as it falls, so I'll call this the beginning point, after a little while it would have fallen maybe down to here. And of course, in the direction it's falling, the waves would be crunched together, so this is a Doppler effect. And in the direction it's going away from, and so that's the, maybe the observer is the holder here. I haven't read the whole problem, but this observer, the person who dropped it then, is going to perceive a slightly different frequency. It would be a lower frequency or a longer wavelength because the source is moving away from that observer. And I think that's where this problem is going. It says, how far below the point of release is the tuning fork when the waves of frequency 485 hertz reach the release point? Take the speed of sound in air to be about 340. Okay, now this is kind of interesting because the first thing to notice is it is a Doppler effect. So what I'll call the real frequency is the 512 hertz. That's the rate at which this metal piece goes back and forth. And so this metal piece here would be 512 hertz. But because it is moving downward or away from the observer, there's going to be a shift in the frequency, a lower frequency, and they want us to know when it is 485 hertz. But there's a little subtlety in here that we need to be careful with, right? It says, how far below the point of release is the tuning fork when the waves of frequency 485 reach the release point? Okay, so we can figure out using the Doppler how fast this has to be going in order to create waves that will be heard back here at 485 hertz. Okay, but then it's going to take a little bit of time for those waves to get up here. So this tuning fork is going to drop an additional distance beyond that. So the tuning fork is going to be down here before this person hears it. So we've got really two factors to consider. The first one is, how much time and how far does it have to fall in order for it to generate waves that would be at this frequency. Now, perceived waves at that frequency is a better way of saying it. But then there's this delay time. The fancy word in physics is called the retarded time, because then there's going to be a time for these to get back up here. Meanwhile, this is going to be falling an extra distance. So maybe I should call this time 1 and time 2. It corresponds to what I'll call a D1 and a D2. And the total distance is going to be D1 plus D2. And the total time is going to be T1 and T2. Okay? And now I need to come back and read it. Did it ask for time or distance? How far below? Okay, so I'm after the two of these together. And let me just read it carefully again. How far below the point of release is the tuning fork when the waves of frequency 485 hertz reach the point of release? So yeah, I think I read it right. So I'm gonna figure out this first part and say, well, how far down is it? And once I get that, then I'm going to figure out how much time it takes to get back up to here, which is going to allow this to fall a little bit more, and that's going to be the total distance. All right, so let's just do that the first part of this problem here and figure out then just how far below is it by the time we get to that spot. All right, so let's talk about the Doppler effect again. What we call the perceived frequency is the original frequency and then shifted. And the shifting has to do with the speed, either the speed of the observer or the speed of the source. I like to use the absolute value and say, okay, if the waves and the observer are coming together, there would be a plus sign. And so I will use that upper sign to say when they're working together toward each other, then, okay, it's going to be a plus sign. And then likewise, if they're coming together, and the source is moving, it shows up a little different because of the shift in the wavelength, not in the shift of the speed. That was kind of in the derivation, but it would be a minus sign. And the other thing is if they are moving away. And that's going to be our goal here. And so there'd be a minus sign and a plus sign here. All right. So for our particular problem, since they say the observer is back at the release point and the tuning fork is dropped, they would be moving away. So we don't want them moving together in any way, so I can cross out the upper sign. So the plus and the minus, I'm going to get rid of. And in fact, we could even cross out the speed of the observer because the observer, kind of implied here, is not moving. So for this problem, it boils down to this. The real frequency, 512, would then be the velocity. So there's the 340. I'm just kind of grabbing my calculator, and I just realized my calculator is in another room at the moment. But I think this one is going to be just fine. Okay? All right. We'll use it. Okay. So the real frequency is 512. The velocity is 340. Let's put a 340. And then it's going to be plus, and let me just try to solve for this last piece here. What is the absolute velocity of the source? It's going down, so clearly it's negative, but I'm going to do the absolute value. Then the perceived frequency, they say, is 485. So this will tell me how fast this has to be moving in order to get the frequency of 512 to shift to 485 here. So the first bit of my mathematics will take the 485 and divide it by the 512, and coming up with 0.947 equals, then I'll go 340 plus the speed, and I'm just going to drop the absolute value sign. But remember, I'm going to get a plus sign here, okay, even though it's going down. Let's see, maybe I'll move this to the other side. So there's 340 plus the velocity of the source would be 340 divided by this 0.947. So let me do that, 340 divided by my last answer. And so this is 358.93. Continuing on then, the velocity of the source would be when I subtract 340 from it. Ooh. And maybe this isn't such a good calculator to use. I knew there was a reason it was sitting up there. Well, I guess I could do this in my head. 340. This must be 18.93. Actually, I guess I can read it here. 18.93. Let me clear that. Okay, so there is the velocity of the source. Okay. Now, let me really turn back to Physics 121. And maybe I better put a page number 1 here. Because I could then figure out, now that I've got the velocity of it, the time. Because we know final velocity is equal to initial velocity. Maybe I'll put an I for initial. And acceleration times time. Okay. And so if you drop it from rest, we're talking about a zero speed. If I'm looking for the positive or the absolute value, let me just put a positive 9.8. The time it takes to fall is what I'd like to find, and it needs to be going 18.93. So this would give me what I called time number 1. Okay, so 18.93 divided by 9.8 gives me 1.93 seconds. So this is, again, what I would call time 1, the time to fall there. And I can also use that in what we often called kinematics equation number 2 to then figure out, well, how far is this? Okay, and so starting at position 0 with 0 speed, but having an acceleration of 9.8 and falling for 1.93 seconds and squaring it, I can get how far. So 0.5 times 9.8 times the answer squared would give me a distance of about 18.3 meters. And maybe I shouldn't put a box around it, but that's this distance of how, excuse me, how far it's gone down. Now remember, then it's going to take some time for the sound waves to come up. Now they go pretty fast, so it's not going to be much time, but there's going to be an additional fall time and an additional distance. So this is not the total time. We still got to mess with page 2 here. Okay, but let's figure out the sound going back up. And I'm going to go ahead and use the kinematics equation number 1 again. Although, sorry. Number 2, distance equals initial plus initial speed times time plus 1/2 AT squared. Okay, but now, instead of applying this equation to the falling tuning fork, let me apply it to the sound coming up. So let me just kind of say, okay, when the tuning fork gets to this position, which I guess we decided was 18.3 meters down, let me just say that new position is position 0. So I'm kind of like going to restart my grid. I'm going to call this a 0. And then the sound waves are going to be generated and go up. So they're going with an initial speed of 340. And I'm trying to figure out this time it takes for them to go up, because that is this time number 2. How much time does it take? So I'll put time 2. Okay. And the sound waves are not a mechanical object. They don't have an acceleration here. They're not free falling. And we know that sound waves always travel with a speed of 340. So that means their acceleration is 0. And so I'm really asking, how much time would it take to get to 18.3? And so, again, this is more of a physics 121 problem here. But you can see all this 121 stuff comes back to us. That's why, of course, the prerequisite for this class is our mechanics, so we can kind of apply all this stuff. Okay, so this says there is an additional time, not much, of 0.05. Why don't I just go, how many decimals did I have over here? 2. I'm going to take one more. Didn't really carry it over here. But there's that extra amount of time. So what you might say then is the total time that this tuning fork has been falling is the original number we got, the time we figured it took to get to this point to having enough speed to produce waves that would then be shifted just enough to represent 485 hertz. So that was that 1.93, which gave us that speed of 18.93. Okay. And then, of course, now we're discovering that it's not much, but there's an additional amount of time needed, and it's still in my calculator, for the sound waves to go up. So I'm going to add 1.93 to that. And I get a total time of 1.9... And let me call it 8.4. I guess I didn't need a calculator for that. It just makes an 8.4. But let me call that the total time. There's some question. I probably didn't do my units, significant figures, quite right there. But now I can come back and say, all right, let's recalculate where the tuning fork is after this total amount of time. And I'll just put total time. All right. So let's rethink about this tuning fork. Now that we've dropped at a total time of T1 plus T2, how far down is it? All right, so again, thinking of the tuning fork, it's starting at 0 with 0 speed because you drop it, then giving an acceleration of 9.8. And I'm not going to put a minus here if it's okay with you. I'm just going to call essentially down positive. Okay. And then this is the total time, 1.984 squared, and that will be the total time down. Okay, so 0.5 times 9.8 times that last answer squared gives me a total distance down of 19.3 meters. So that little bit of extra time looks like, because before we had 18.9 meters, is 1 extra meter. So it'll fall just a hair more. A meter's quite a bit, but it's going pretty fast by that time. And so the sound's got to go all the way back up, 18 meters up, allowing the tuning fork to drop or fall another 1 meter. All right, hope that helps.